Hello everybody, today I'll give the class lecture on carbanions. Okay. A carbanion is formally defined as a carbon species, anionic with a negative charge located on the carbon atom. So they are negative charge organic compounds. They are mostly conjugate bases in the sense of prostate senses of organic compounds. So they are formed by the deprotonation of a carbon atom. So we can say, I can write down here, a carbanion is formally defined as a carbon species, charged reactive intermediate, okay, charge intermediate with a carbon species with a negative charge, located on the carbon atom, okay. So they are a negative charge compound species, and they are very reactive. So they have as like a nucleophilic reagent, okay, they are nucleophile also. They can be formed, they are conjugate bases of, or conjugate bases in the Bronsted acid base theory, okay, Bronsted sense of organic molecules, This is the behave as an cis organic having CH bond, okay. So molecules that are formed by these carbanions are formed by deprotonations, You can see deprotonation of a carbon atom having say CH bond, okay, having CH bonds. So I'm repeating again. A carbanion is formally defined as a carbon species, charged reactive intermediate with a negative charge located on the carbon atom. They are conjugate bases in Bronsted acid base theory, or when that are formed by the deprotonation of a carbon atom. Say for example, I'll give example here, CH here, by base to the proton. So you can give it like this. So you have carbanion here plus BIs. So you can say sit here. So this way you can form. Another way that carbanions are linked to organometallic chemistry. Basically, they are usually used in organometallic chemistry also. When they are these carbon atoms are linked with many organometals like very electropositive. Then, for example, alkali metals. When carbon atom is linked with a electropositive atom, like alkali metals, then they behave as a carbanion. So I will give some example. Okay, I'll write down here again. Carbanions are linked to. The carbanions are linked to organometallic chemistry, okay. Organometallic chemistry. So when the carbon atom is attached to a more electropositive metals. Say for example, alkali metals, okay. Then the then the carbon behaves as a carbon ion. For example, say, giving here, link with the metal, where M is the metal, okay. Like metal, electropositive metal, for example, alkali metals. So they can have as a link with these are used as ionic polarity as delta negative and delta positive. Okay, so after link this one, then you can have negative charge here, M is positive metals. So like this. So they are linked with the metals, then they behave as a having a metal will have the highly electropositive, and then carbon atom, then this carbon becomes acting as a carbon ion. So we have two types of you can have two types of carbon ion formation. Okay. So when they are linked with the organic metal, when they are linked with the metals, electropositive metals, they can form the carbon ion, and they also can be with when the hydrogen atom is deprotonated from the organic compound, then we got the carbon ion also. Okay. Now let's come to the generation of carbon ions. Generation of carbon ions can be generated by two methods. Okay. Generation of carbon ions. Generation of carbon ions. Carbon ions can be generated by two types. The first one is by removal of an atom or groove without its bonding pair of electrons. You can say this. Another one is heterolytic fissions. This is heterolytic fissions. Fission, just like carbocations, we have to study also. So here, this is one of the most general method for the formation of carbon ion by removal of an atom or groove from carbon, leaving the bonding pair behind. So for example here, the X is the leaving groove, so it gives groove like this. So plus X becomes positive charge. Okay. So the X lost by giving without this bonding pair electrons, so it gives like this. So this kind of reaction you can found in carbon acids and lead gases. We have discussed this base reactor. So base abstract the photon. So we can have this also carbon ion. We discussed the pH. So this is carbon acid having CH bond, and this is base abstract, and then we got a carbon ion. Okay. So this is by heterolytic fissions. So by heterolytic fissions, we can get this carbon ion where the leaving group loses without bonding pair electron. So this is one. Many examples are here. Not only the decarbonization also can take place. Carbon dioxide may be lost, a group of carbon dioxide may be lost, or chloride also lost. So some examples are by decarbonization also you can have. So like this, decarbonizations by this one and then this one. Okay, negative charge plus carbon dioxide. So this can be also formed. So for example, one example is this CO2. Okay. So they are metal. So it comes like this. So it comes like carbon ion is formed. Okay, plus carbon dioxide. Or chloride also can be lost. So I am giving examples. This one and sodium in amalgam, mercury. So you can lose this CH3 carbon negative charge plus sodium also. And then the highly ion pair formation takes place in this case. So these are the generation of carbon ions using this by heterolytic fission. So heterolytic fission takes place. So the living grooves lost without the bonding electron pair. Then this is a fast method. So here carbon ions are generated by loss of atom or group atom without bonding pair electrons. So this is heterotic fissions. And second method is by addition of a negative ion to a carbon-carbon triple bond. Second method is by addition of a negative charge, we can say negative ion, or to the carbon-carbon multiple bonds. Okay. So here, let's say many examples is double bond here. When an ion attack here, so you lost like this. So we got this is nucleophile, or it can be nucleophile, negative charge and ion. So here we got this Y here. So and we got generated the carbon ion here. Or triple bond also, similarly triple bond Y can attack. And you got this. Okay, C, okay, negative charge, double C, Y like this. Okay, so this, in this way, addition of an ion or negative charge ion to the multiple carbon multiple double bond or triple bond, you got a carbon ion. So these are about the generation of carbon ion. So I'm repeating again. The carbon ions can be generated by two methods. First one by heterotic fission, that is by ring cleavage, by bond cleavage between the carbon, hydrogen, or some other atom, where the atom leaves without the bonding pair electrons. And another one is we can have this one. Second method is by addition of a negative ion to the carbon-carbon multiple bond. So here double bond attacked by an ion or a negative ion, and triple bond attacked by negative ion. We got this one, these two carbon ion. This is vinyl carbon ion. So now let's come to the structures of carbon ion. Okay, structures of carbon ion. Structure. Generally carbon ion is sp2 hybridized pyramidal structure. It has like this. You can have pyramidal structure, two lone pair electron discussed, and then we have, so let's say R1, R2, R2, R3. So here generally carbon ion exists as a structure of carbon ions are generally sp2, sp3 hybridized. They have sp3 hybridized and a pyramidal structure. Okay. So generally, simple unsubstituted alkyl groups, they can be formed by this. They can be formed from this type of compound, R1, and then R3, R2. Okay, by reacting with pairs, so you can generate it like this. Loss of proton, got this one. So they can be derived from sp3 precursors. This is sp3 carbonate, okay, compound. So generally, structural carbon ions are sp3 hybridized pyramidal structure, but they can be also deviated. Some deviation can take place from these structures. So for example, vinyl carbocations, vinyl, as we have discussed earlier. So vinyl R1, R2, R3. So here vinyl is here the sp2 hybridized, okay, sp2, and they are planar also. They can be planar. Okay. Then we can have another one from triple bond. Okay, R here also. This is sp hybridized. Okay, this one sp2. This is sp hybridized. But vinyl compounds, they can have, so can be denoted like this. So you can have these two vinyl. This is allylic system, allylic carbon ion. So they can have negative charge here, and then okay. So they are all sp2. Here is sp2, allylic sp2 hybridized. Here planar, okay, sp2 hybridized, planar. But in the case of generally carbon ions are generally sp3 pyramidal structure. So there are some deviations are here in the case of vinyl, styrenic, allylic carbanion. So they can have this type of sp2 hybridized sp. Okay. So these are I'm giving some example that they can be deviated from the general structure. So generally carbanions are sp3 hybridized pyramidal structure. Okay. So now let's come to stability of carbanions. Stability of carbanions. Stability of carbanions. So that's opposite to the carbocations. Okay. They are generally tertiary or least, primary or more here in this case. So by definitions, every carbanion process, I'm writing okay. By definition, every carbanion process and unshaped electron, that is they are necrophilic in character, and therefore they behave as a base. Okay. So by definition, every carbanion possesses an unshaped carbanion possesses an unpair of electrons. Unpaired electrons. So they behave as a and the electrons should behave as a and X as a base. That means they are necrophilic character. Necrophilic in character. Okay. So there every carbanion they can show the stability of the carbanion is directly related to the strength of the conjugated states. So when the carbanion accepts a proton, it becomes carbanion when accepts a proton, it becomes a conjugated state. So you can write down here carbanion can accept a proton to act as a and the conjugated state to act as a conjugated state. Okay. When carbanion accepts a proton or receives a proton, becomes a conjugated state. So the stability of the carbanion depends on the strength of the conjugated states. Okay. So what I want to say that carbanion can accept a proton to become a conjugated state. So the stability of the carbanion depends on the strength of the conjugated state. So weaker the acid, the greater the base strength, weaker the acid, greater the base strength, and thereby the stability of carbanion is lowered. I'm repeating again, the stability of carbanion, the stability of carbanion depends on the is directly related to the strength of the acid, to the strength of the conjugate acid. So stability of carbanion depends on the conjugate acid. Okay. Okay. The weaker the acid, weaker the acid, weaker the acid, weaker the acid, the greater is the base strength. Strength of the base increases. Okay, the base if the conjugate acid is weak, then the base strength is more, and thereby the lower stability of the carbanion. Stability of the carbanion. So weaker acid means stability of carbanion is weaker. So first point is stability of carbanion depends on the strength of the conjugate acid. Weaker strength of the conjugate acid. So first point is the stability of carbanion depends on the stability of the strength of the conjugate acid. So weaker the acid, the greater is the base strength, so the lower the stability carbanion. Weaker the acid, conjugate acid means weaker the stability carbanion. Okay. So first one is the stability of carbanion depends on the strength of the conjugate acid. Now, then next is the second one is the effect of S character, S orbital character of carbon center. Okay, carbon center of the carbanion. So if the X character is more, then stability of the carbanion is more. So here stellinite is greater than, then we have R2, C double bond, C, okay, vinyl, then we have alkyne carbanion. Okay, so stellite, acetylite, so S character is 50%, S character, and here is vinyl carbanion having 33% S character, and here is alkyne carbanion which has 25% S character. So greater the percentage of the S character, greater is the stability of the carbanion. Just because here in the increased S character means that the S orbitals are closer to the nucleus than the corresponding p orbitals. So thereby bringing unsharp pair electrons towards the carbon atom. So that's why this 50% S character of stellite carbanions are more stable than vinyl carbanion having the 33% S character. And they are more again, this alkyl carbanion are least stable because of the 35% S character. So this is about the effect of S character, second one. Now third one is about the inductive effect, stabilizing field effect. Okay, inductive effect. Third point is stability of the inductive effect. Carbanion depends on CH3. Just opposite this we have discussed carbocation. Then we have R2, CH, then we have R3, C. So primary, secondary, and tertiary like that. This is our primary, secondary, and tertiary. So this is opposite to the stability of carbocation. So in the effect here, carbanion, in the case of carbanion, methyl or primary carbanion more stable than secondary carbanion or more stable than tertiary carbanion. So this is what this is explained by inductive effect. And third one is conjugation with a double bond, multiple bond. Conjugation effect. Okay, this is similar with we have discussed in earlier cases in the carbocation. So I'm just giving it a bit faster. Okay, because we have discussed in the carbocation case. So when carbanion is conjugated with a double bond or multiple bond, so they are more stable because they have more canonical structures. Say here, allylic carbocation, I can have allylic carbanion here. Okay, this is allylic carbanion. So they can delocalize. So they can more resonance structures. So you can have say allylic carbanion. So we conjugated with a double bond, so it can get delocalized. So more canonical structures is more stable. So similarly you can have benzylic carbanion CH2. Okay, let's say this one, benzylic carbanion. So you can have many canonical structures. So it can give more stable. So here you can have stabilized this way. So you can have the bonds CH2, negative charge here. Then we have here again delocalize this way. Then we can have CH2, the bond here, negative charge here. Then again delocalize this. So this way we can have so many And here again coming back again. So in the canonical structure we can write hybrid structure. So here CH2 and negative charge here. Okay, negative charge. So this is a more joining structure means more stable as in the case of carbocation. Okay, so when I'm repeating again that stability of carbanion depends on the conjugation effect. More conjugation means more stable, more joining structure. So more joining structure means more stable of the carbanion. So another case is about the another effect is about the aromatic effect of aromaticity. Another one is effect of aromaticity. Aromatic compounds or aromatic carbanion can also have more effect of aromaticity. So aromatic carbanion can also get more stable because they can have. So for example, say I'm giving one example. So here, okay, this is pentadiene carbanion. So you can have many structures. This carbanion can be generated. So you can have many structures, canonical structures. So you can have this way. Again, this one like this, and so on. You can have. So you can have here negative charge here. Again, this like this, and so on. So we can delocalize in many ways. So if it is aromatic compounds, you can give more aromatic. So hybrid can be written less. So this hybrid can be written less this way. So this hybrid of this aromatic compound is aromatic. So 1, 2, 3, 4, 5, 6. So you put by Hankel rules. It is 4 and plus 2 rule for that. So it is an aromatic compound. You can say cyclopentadienyl carbanion. Okay, this is non-aromatic compound. I'm giving one example. The effect of aromaticity is more stable because of the presence of so many joining structures. And finally, effect of the sulfur or phosphorus substituents. Okay, effect of sulfur or phosphorus substituents. Sulfur or phosphorus substituents. When a carbanion, the negative charge of the carbanion is linked with a sulfur or phosphorus substituent, then compound itself is the carbanion itself becomes more stable. For example, say peratol sulfonate or like that. So here peratolin type, sulfonate type. Okay, here sulfonin groups is linked with a carbanion, or let's say methyl or ethyl, like then they can be delocalized this way. So we can have joining structure. So when you link with a sulfur compound, then you can delocalize this way. Okay, Me, Et. Similarly, you can have another one. You can have also this way. This also you can have this, and here also you can have. It becomes this side, and here you can have one negative. So in this way you can have canonical structures. So it is linked with the sulfur or phosphorus, so you can have another phosphorus. You can have, say, examples like phosphorus. In case with phosphorus there, when linked with phosphorus, CH3 and phosphorus, double bond O negative charge, and this Me here. So you can delocalize this way also. So you will link with phosphorus when the carbanion is linked with a phosphorus or sulfur atom, then it can be delocalized this way. Okay, so it is also stable. So one of the stability is that the effect of sulfur and phosphorus substituents, O negative, CME. Okay. So you can see, no problem. Okay. So here, what I'm trying to say is the negative carbanion, the negative center is linked with a sulfur or phosphorus substituent. There also stability of the carbanion takes place. So these are about the today we'll wind up here. So next class we can have reactions, rearrangement of the carbanion. So I'm repeating again today. Carbanion can be the negative charge, nucleophilic in character, and their structures are sp3, a pyramidal structure, but they can be deviated by sp2 or sp, depending on the structure of the compound, or a sterylene compound or phenolic compound, like that. And they can be generated by two methods, by heteroactive fissions and by addition to a carbon-carbon multiple bond. Okay. So we have discussed this so far, and stability depends on first one is the effect on the strength of the acid, conjugate acid. So weaker the conjugate acid, the lower the stability of the carbanion. And second point is the we have discussed the stability is the S character. More S character, more stability of the carbanion. Okay. Then we have this inductive effect character. Inductive effect of the inductive effect. Primary are more stable than secondary, more stable than the just opposite the stability of carbocation. Then we have conjugation effect. More conjugation, more chemical structure means more stable. So this way, then we have substitution effect, aromaticity effect, like this. So today we will wind up here. Okay.